Madea from Open. And it is my great pleasure as the Associate Dean for Science here on North Campus to introduce our senior professor, Dr. Madea, who last semester as an active full-time professor at Broward College. She is retiring at the end of this term. But hopefully she'll come back and play with us some more and do some great chemistry demonstration. So please welcome her, and you will be amazed, and you'll all become chemistry majors. This was dumb. I was a kid, I thought you would have done chemistry. All right?
Well, thank you.
Enjoy.
Welcome, everybody. Sorry for a little bit of delay, but we will get going. So today I'm going to talk about basically the magic of chemistry, what chemistry is. So even if you don't want to, you can learn something. But first thing I'm going to do is welcome you. Would you bring over the other side, please? The theme at the top of today's demonstrations, I guess, is the magic of chemistry. And I sometimes tell people that if I had been born a couple centuries ago, I'd probably be burned at the stake by now, for some of the things that we do. Because what you're seeing, we can call it magic, and it's fun and whatever, but let's see what. So, it is chemistry magic. No, it's messy. No, it's science. So, again, we'll do this other way. So the idea here is chemistry is the science. Chemistry is the science of matter, the study of matter, everything that makes up our world. Some of you will get this, the others might get it a couple days from that later. I saw a T-shirt that says, "Don't trust atoms, they make up everything." So everything that makes up our universe is either a mixture, hit the button, chocolate chip cookie, lots of things going on in there, or elements, things that make up the most basic building blocks, and are represented in the periodic table. Again, this beautiful periodic table that raises our wall outside. 10 years ago, a group of honor students, and I made that, and I'm very proud of it, that long after I'm not here, that periodic table is still there, and in all its beauty. Then we have compounds, or atoms, basic building blocks of all things. Go into some fun stuff. Then these things called compounds, which are elements joined together, or the more complicated things that make up our world. So, again, we just get lots of different combinations here, things as simple as water, carbon dioxide, salt, sugar, DNA, etc. Molecules are bigger particles made up of atoms joined together, and some of them are really, really big molecules, like proteins and things that get into living systems, biochemistry. But what I want to focus on today is not what matter is and what makes things up, but how things change. Because to me, that's the essence of chemistry, and that's the beauty of chemistry, are what we call chemical changes or chemical reactions. So let's see. This is a very classic paint team of the famous alchemists. Alchemists were the forerunners of chemists. The alchemists, those of you who have taken classes know this, were still holding on to the ideas of Aristotle, that everything's made of earth, air, fire, and water. They didn't understand they had not yet figured out that things are not made that way. The alchemists were manipulating matter. They were trying to, in many cases, turn lead into gold. They're trying to make themselves wealthy by finding the secrets of things. They were on a fool's mission. They were never going to get it right because their underlying theory was incorrect. But along the way, they did discover some important things that still have significance in modern chemistry. They discovered many of the things that we now know are elements. They made up, created a lot of the glassware that we use. And they invented processes such as distillation. If it weren't for the alchemists, you would never be able to drink anything stronger than beer or wine. So think of them. This is a famous picture of an alchemist named Broward in Germany who was discovering the element phosphorus for the first time. The name phosphorus comes from the word for light, because phosphorus has this wonderful quality of glowing in the dark. So he's kind of fascinated by the whole thing. Let's see what we have next. So what is a reaction? In a chemical reaction of change, atoms rearrange into new patterns, forming new bonds. New substances with new properties are formed. How do we know when something happens? How do we know that a chemical change has taken place? Well, is there a color change? That's a real good clue. I'm not talking about taking grape juice and pouring water in it and making it less purple. I'm talking about something that was yellow and now it's green. Or what you saw in those signs, that was a chemical change. This is also an example of a chemical change. If you were to, I would ask you what color that is, you would probably say yellow or orange. Whatever. Now it's red. Now it's green. We call that the chemical traffic light, because just like a traffic light, it goes from yellow to red. No.
Red, yellow,
Yellow, red. This goes backwards, and it's an ugly way it's doing it. This, again, is a chemical reaction. Now, inquiring minds want to know, well, what is that? Well, if I told you that it was a solution of sodium hydroxide and dextrose with an indicator called indigo carmine, what does that do for you? Okay. It's a chemical reaction in that things are, and those students in my 1040 class, we're talking about moving those electrons around. The elements letting go of one partner and teaming up with something else. Okay, so that's what's happening here. And an indicators are chemicals that change color when you've probably heard of acids, or the chemical opposite of acids or bases. Indicators are chemicals that change color in the presence of acids or bases. So what's happening here, again, we'll go back to being yellow, was that when I shook it a little bit, the sugar in there, the dextrose, also called glucose, reacted with the oxygen in the air a little bit. When I shook it a lot more, it reacted with more oxygen and became even more acidic in this case. So again, the idea here is color changes. Does a gas or solid form where there was none before? We'll see some examples of that. A good hint that there's a chemical change. I'm not talking about just the bubbles coming out of the can of Coca-Cola, but when you mix things together and, well, I could do that. This is a very simple one that many of you might be familiar with. This is chemical name sodium bicarbonate. Anybody? Baking soda. Baking soda. You just pay a lot more for it here than. And this is a 5% by mass, only 41 students, 5% by mass solution of acetic acid, also called And you see a chemical reaction in which gases are being formed, a gas, in this case carbon dioxide. I guess kids use this to make a volcano or whatever. That's pretty exciting. It's a good way to clean out your garbage disposal, get smell better and stuff. But that's a very simple and you can do this one at home, chemical reaction. Also, is there a temperature change? Chemical changes always involve energy. In fact, all changes involve energy, not just chemical ones. So if you detect an increase in temperature or a decrease in temperature, it might be a clue that there's a chemical reaction. But you can't be sure, because sometimes just physical changes also involve temperature change. So we're going to look at types of chemical reactions. That's not me when I was 12. Okay, the simplest type of reaction is what's called a synthesis reaction. It just involves elements, so empty is magnesium reacting with oxygen. That's one example. This is where we can turn the lights on a little bit. Most of the elements are a little bit more up here. Sorry, we should focus on it first. Yeah. This is a piece of magnesium. Magnesium is a metal. Most of the elements in the periodic table are metals. This is magnesium ribbon. Magnesium is very low in density. Many chemical reactions don't happen until you supply energy. You've got to give things a kick to get them started. So the magnesium right now is in contact with the oxygen in the air. Oxygen molecules are slamming into the surface of this magnesium, but they're not doing anything. The oxygen atoms are too busy holding on to each other. But if I supply some heat, and as they tell you, don't look directly at that. Right, look at all this stuff. Okay, when I get my eyesight back, that's a reaction. Many chemical reactions are what we call exothermic, which means they give off heat. So obviously, when you see something like that, magnesium burns, which means combining with oxygen, and forms that intense white light. Magnesium is used in flares. It used to be used in private multi-guns. Remember when cameras had flash bulbs? You can ask your grandparents. It won't even burn underwater. Now, when it burns, it's not magnesium anymore. It has turned into a new substance, this thing called magnesium oxide, the white powder that you saw. So, again, a little bit more light here. And let's move on to the next one. So, synthesis reactions are just elements combining. Decomposition reactions. Okay, there's one. Anybody know what that first compound is? H2O2. It's this hydrogen peroxide. Water is H2O, which is the most stable compound that hydrogen and oxygen form. They also form this other compound, hydrogen peroxide. Hydrogen peroxide is very, very reactive. You can buy it in Publix, you can buy it from Walgreens, but what you're buying is a 3% solution. So in other words, it's 97% water. This hydrogen peroxide is 30% hydrogen peroxide. So it's 10 times more concentrated. So that's not what I do. That's what's going to react. What we're going to see here is the decomposition of hydrogen peroxide. But to make it more visual, I'm just going to put this. This is just laundry detergent. I'd rather do this than my laundry. Okay, so this is just laundry detergent. It is there for dramatic effect. Now I'm going to pour on the hydrogen peroxide. Notice the chemist never sets down the top. You see what I'm looking at? I mean, does that not look cool? Is that not, I mean, whatever. And it's very practical too, because when I set the top down, I could contaminate what I'm setting it on, or I could pick something up that when I put the top back on, you know, so I can do this like when I'm opening 5 lights. Now what I have right now is just wet soap, and that's not very exciting. But chemists know all sorts of tricks. Chemical reactions can happen when you put certain things together, but sometimes they're very slow. Sometimes you need energy to kick them up, like heating up the magnesium. Sometimes the reaction is just too slow to be noticed. So there are certain chemicals that behave as what we call catalysts. And catalysts are things that make a chemical reaction go faster. Every cell in your body has catalysts in it, right? Because at body temperature, the reactions you need to stay alive would be way too slow to keep going. So the catalysts, we call them enzymes in living systems, cause the chemical reactions needed for life to happen at the rate that's needed to happen. I'm going to add a chemical. It's something called potassium iodide. Nothing magical about it. It's just a type of salt. I'm going to put some potassium iodide in there. Look at it. Just look at everything that's happening. 10-41 seconds into effect. Now, when the reaction happens with the catalyst, the hydrogen peroxide broke down into water and pure oxygen. So the bubbles you're seeing, the fact that this foamed up, was because of the bubbles of oxygen, which again became more dramatic because of the soap. You saw the evidence of heat. It was very, very hot. In fact, it was so hot that the water was leaving by steam. So what you saw leaving was the steam. So this is an example of a decomposition reaction. Hydrogen peroxide breaking down hydrogen and oxygen. Now, when you use hydrogen peroxide at home, again, a much more diluted solution. When it hits the warmth of your skin, especially if there's a cut, because we use hydrogen peroxide to kill germs. There's an enzyme in the blood that speeds up the decomposition, and you get the bubbles of oxygen, and it's the oxygen that's killing the germs. You would never want to put this stuff. This is 10 times too concentrated. But it's the same chemical reaction happening when you use hydrogen peroxide. Look at the last reaction here. Looks very, very complicated, but notice that it is a decomposition. You're starting with one compound, a very complicated thing, and it's breaking down into different things. Okay, I didn't bring that with me today because dynamite. So they don't do this stuff. Yeah, maybe my retirement party. There are more elements to this. Again, chemical reactions can be very colorful. They can be very explosive. They involve energy. If they react very fast and a whole bunch of gases are formed, then you have the expanding gases that are not holes in atoms and not bubbles. Okay. The next category is combustion or burning. So something as simple as C4H10, which is a chemical forming for butane, which is in a lighter like this. So that's a chemical reaction represented by that first equation. We already saw the magnesium burning. That's also a combustion reaction. And I'm not going to set any iron on fire, but iron will burn. And remember, some chemical reactions are very fast, especially if we give them a kick. Some are very slow. So the next picture shows the slow reaction between iron and oxygen. So rust. Whether it happens slowly or whether it happens rapidly, like the burning of magnesium, it's still combustion. And with the 20% content of oxygen in our air, it's almost impossible for things not to be reacting with oxygen. Some of them can be a kickstart. Some of them happen very slowly without any outside interference. Okay, let's see what comes next. Single replacement reactions. This usually involves a metal with a compound that contains another metal. Look at this represents copper, and this represents silver. Now I'm going to do that reaction, but it's a very slow one. This is a solution. We work mostly with chemicals that are dissolved in water. So this is this Ag silver nitrate compound. Silver compounds react with light, so we keep them in bottles away from light. So I'm just going to pour the silver nitrate in there. One thing you might notice, and I'll point out, you can't tell what something is by looking at it. Right? I mean, that just looks like water. So it's very important in chemistry that we put labels on things in our own private language. So that is water with this compound in it. I'm going to take a piece of copper. This is just plain copper wire. Now this is not going to happen right away, so we're going to come back and look at it. But right now it just looks like a colorless solution with a piece of copper. The second one, I really should put in my bottles, is a reaction of that HCl, and the second one is hydrochloric acid. Pour some of that in here. It's not very concentrated, it's just, for chemistry students, 1 mole per liter. And I'm going to put some metallic zinc. Zinc is obviously a metal. This is nice, shiny, fresh zinc. The zinc reacts with the oxygen in the air and it gets a kind of a dull white coating on it. Zinc is used to put over other metals to keep them from corroding. Have you ever heard the word galvanized? It means that they put a coat of zinc on something. So like they can make a can out of iron or steel, and iron, of course, corrodes and breaks off and falls apart. But if they put a layer of zinc on it, so I'm just going to pour some of the zinc into the acid. Sorry. I should have asked for very concentrated acid. calcium. Now, I mentioned calcium. What color do you think? White. Milk, bones and teeth and things. Well, calcium is not white. Calcium is it's actually a gray metal. You can't see this very well. It's actually a gray metal. It's very, very reactive. So right now it's undergoing a change even with the oxygen in the air. I'm going to put this gray, it's very powdery calcium metal into water. Can you hear it sizzling? It's releasing heat. Yes, but it's look at the equation. What's that? Hydrogen gas. Okay, now it's really good. It's a very exothermic reaction. It's releasing hydrogen gas into the bubbles you're seeing. And now it's white. Calcium compounds are white. When calcium is combined with other things, it's white. But when it's by itself, it's a silvery gray metal. Okay, let's see what's next. The next one are double replacement reactions. These look more complicated. But we already saw one of these. So let's first yeah, these are big, kind of hard to hold, but I want you to be able to see it. This is a solution of the compound Ki, which in chemical jargon means potassium iodide. This says Pb. NO32. What's Pb? Lead. This is a compound of lead. Well, it's water with a compound of lead in it. Okay. When I mix these together, you see a very striking color change. Yeah. I can't see through it anymore, right? I could see through that, and I can't see through this. That means there's something in there that can't dissolve in water. And if I leave it alone, that's going to settle to the bottom. We call that a precipitate in chemistry. And that was one of the clues, remember, about a chemical reaction, was does it form a solid which sinks to the bottom. Lead forms a lot of insoluble compounds. Lead forms some very beautifully colored compounds, which don't fade in sunlight. They don't, they stay very true to bright colors. Lead compounds have been used for paints, for glazes on pottery ever since Roman times. But lead compounds are extremely toxic. And we don't want to get lead into our system because those lead atoms are very big. They stay in our body. They're what's called cumulative, and they can cause nerve damage, insanity, infertility, all sorts of things. So commercially, companies don't make compounds, they don't make paints with lead pigments in them much anymore. Artists' paints do. They still have lead in an oil base for your oil paints. But for home painting and stuff, paints with lead in them are no longer allowed to be sold. Sometimes people buy very, very old houses, and the walls start, the paint starts chipping off, or they remodel it, and they kick up a lot of lead dust from the paint. It can be very, very destructive. The second one is a similar compound, again involving, I'm going to hold it this way, potassium iodide. And I'm going to pour this into this compound, mercury chloride. And that's this reaction. So Hg is mercury, but chlorine, mercury chloride. And notice, for those of you who care, notice how the iodine and the chlorine switched. Potassium was with the iodine, now it's with the chlorine. Mercury was with the chlorine, now it's with the iodine. And that's what you're seeing here, is that mercury compound. Now, this is worth the whole. That is it. No, it's just another chemical reaction. I mean, everything can be explained in terms of atoms bonding and bonds breaking and things, but you get some really, really neat effects with that. So that's a fun one. Okay, anything else? We have oxidation reduction reactions. Next one. Oxidation reduction reactions are a huge category of reaction involving loss of gain of electrons. In chemistry courses, you study that in the first year. And everything from combustion to metabolizing food, to the rusting of iron, to plants growing and producing the colors that they do. Those are all examples of oxidation reduction reactions. They're a huge category of reaction. Let's see what we got here. So one very practical application of oxidation reduction reactions are batteries or voltaic cells. Let's see what we got next. Backup or whatever. I want to, there's something. It's okay. It's okay. There's two things I'm going to take over now. I have one experiment, one reaction yet to show you, but I want to go back to. There's two things I want to show you that. I can get back to it. I want to show you a couple reactions which I don't do because they're I must do this one. Okay, we need to move them. Yeah, we need more volume though. Okay, maybe that's the best we can do. But let's see. This is. What? Yeah. Let's try it now. Well, you have to read it. Okay, a tiny little piece of sodium. The yellowish green is chlorine gas in the pure state. A sodium is so reactive that it will rip water apart and form pure hydrogen and explode. But the heat of that reaction initiated the reaction between the sodium and the chlorine. So sodium is a gray, soft metal. Chlorine is a yellowish-green, poisonous gas. But when they do their thing, which is what that was all about, you get table salt. I'm going to do one more. Okay, let's get the lights off for this one. Now this is a reaction, this is a single replacement reaction between two things that you don't think of as being that exciting. Aluminum. Aluminum is the most common metal on the earth. You might not realize that, but it is. There's more aluminum, total mass of aluminum than any other metal on earth. And the other thing we're reacting with is rust. Now this guy's a real... I did not become a chemist to find men. That is not true. That is not. So he's out near it. He's mixing together the pure aluminum and the He's just going to use the magnesium as a fuse. That's pure iron. There's a better one. Then I'm almost done. This is a good one. Indeed, this is. Michigan State. No. Let me just try one more. This will get involved. I have one more reaction to show you, and we really don't need the blue screens. Okay, first of all, look at what's happened to the solution. It's now kind of blue. Look at the copper wire. That's pure silver. I've grown pure silver crystals. Okay. When I finish, I'll have it up there and you can look at it. But the copper and silver are trading places. So I'm growing silver crystals. So the obvious question is, what are you doing teaching chemistry at Broward College? Why aren't you out growing silver crystals? We've got a millionaire. Okay? Because the silver atoms were there all the time. They were just in a compound that was dissolved in water. You couldn't see them. You can't make an element from something else. All you can do is move things around. And the silver nitrate was a compound that had silver in it. So all we did was take that silver out, and now the silver's by itself. I realize it's really getting beautiful right about now. So we can take a look at that again. Now I have. Let's just pray that the spirits of chemistry are with us today. Lions coming. Okay, this last one. So let's turn off the lights. Let's turn this off. Okay. I want to focus on this right here. Now, all chemical reactions, like I said, involve energy. And sometimes it's very evident, like the flame when something catches on fire. But here's a reaction that the same thing, just doing it slowly over ice. This is a chemical reaction that releases energy, but not in the form of heat, in the form of light. The chemical is a very complicated organic structure that has the common name luminol. And there's an oxidation-reduction reaction going on here. And the energy released in that reaction is being emitted as light rather than heat. There are living things that emit light. In the ocean, you have different jellyfish and algae and things like that. On Earth, we have fireflies, lightning bugs. How do you think they make that light? They're not plugged in with a long cord to power light. They use chemistry. They have little pouches in their body, if you will, that have chemicals. And when they want to send a message to another firefly, they let those chemicals touch. And you get a little flashlight. You can turn the lights on them. It's the same principle in the glow sticks and things like that. That you have to snap first and then the chemicals mix and whatever. This doesn't last as long as those things. But I wanted to end with this because that's my favorite reaction. It's not just chemistry, it's beautiful chemistry. And how can you not be impressed with that and want to know more about what's going on there and how does that explain everything that happens in the world? I mean, I talk about my retirement and stuff. I have taught for 43 years. to spend your whole life learning about why everything is the way it is, why things behave the, I don't know a fraction of what there is to know out there. But I find the world a much more interesting place because I do understand some of it. And I try to pass some of that along to my students. And the more mess you make, the more fun it is. But anyway, so chemistry does seem like magic at times. And the wonderment that comes out of it and the beauty that comes out of it, those are qualities that you can't measure and you can't put on a test and you can't put in a model. And I hope you appreciate some of that and just not, as you study chemistry or any science, just look at numbers and equations on a page and think, oh, this is boring. You actually see this stuff happening.